What if there was something lurking in the cosmos that defies the very laws we've built our understanding of the universe upon? An unseen force or object that breaks the rules of space and time as we know them, so elusive, yet so crucial to grasping the deepest mysteries of existence. The universe holds secrets that challenge everything we think we know, pushing the boundaries of reality itself, hinting at forces and phenomena beyond our wildest imagination. Join me as we take a look at all we don't know about the universe. The dark photon puzzle, a potential bridge between light and dark matter. Physicists have long grappled with the mysteries of dark matter and light. At the intersection of these two realms lies an intriguing concept, the dark photon. This hypothetical particle raises questions that could reshape our understanding of the cosmos. Dark photons are proposed as a means to connect the visible and invisible components of the universe, potentially acting as a bridge between light and dark matter. As scientists delve deeper into the implications of dark photons, they discover that their existence challenges the standard model of particle physics, which has served as the backbone of our understanding for decades. The standard model describes the fundamental particles and forces that govern our universe, yet dark photons introduce the idea of a new particle that doesn't neatly fit into this framework. This inconsistency invites speculation. Could dark photons reveal fundamental gaps in our current theories? If proven true, they could open doors to new physics that extends beyond what we know. One of the most captivating aspects of dark photons is their proposed mechanism of kinetic mixing. This interaction allows dark photons to couple with standard photons, enabling indirect detection through observable effects on light. For example, scientists could measure shifts in spectral lines caused by dark photons interacting with light. This idea has sparked excitement within the scientific community, as it provides a potential pathway for uncovering dark matter's secrets. It raises an intriguing question. Could dark photons be the key to unraveling the mysteries of particle physics? The answer may lie in future experimental discoveries. Diving deeper, researchers are exploring how dark photons might fit into dynamical dark matter models. Traditional models treat dark matter as static, but dark photons could suggest a more dynamic approach, where dark matter evolves over time. This concept has significant implications for understanding structure formation in the universe, potentially offering explanations for the large-scale structures we observe today. The possibility of dynamic models challenges established notions and invites fresh thinking in astrophysics. Connections to the early universe also emerge when considering dark photons. Their interactions might shed light on the inflationary period that followed the Big Bang, a time of rapid expansion and energy fluctuations. If dark photons played a role in this cosmic inflation, they could alter our understanding of how energy dynamics shape the universe's evolution. This idea pushes the boundaries of our knowledge, suggesting that dark photons could provide insights into the very fabric of the universe. Researchers are not stopping at theoretical implications. They are also considering the observable consequences of dark photons. One exciting area of exploration is exotic decay channels. Dark photons could open pathways for dark matter particles to transform into standard model particles, which we could potentially observe in future experiments. What if dark photons could reveal new particles? This tantalizing prospect hints at a wealth of undiscovered phenomena waiting to be explored. As scientists analyze astrophysical data, dark photons may also provide explanations for various anomalies. For instance, certain excesses in cosmic rays or gamma-ray signals have puzzled researchers, failing to align with current particle interaction models. Dark photons could serve as a missing piece in this puzzle, offering explanations for unexpected observations and enriching our understanding of cosmic events. Another intriguing area of study involves the cosmic microwave background, CMB radiation. Dark photons might influence the patterns we observe in the CMB through their interactions. If they do, it could leave detectable imprints that would help us unravel the mysteries of dark matter. The quest to understand the CMB is crucial for cosmology, and dark photons might play a pivotal role in enhancing our grasp of the universe's history. Neutrino physics is also set to benefit from exploring dark photons. The interactions of these elusive particles could provide connections to the behavior of neutrinos, potentially unveiling new insights into this mysterious sector of particle physics. This relationship hints at an intricate web of interactions that govern the fundamental forces of nature, showcasing how interconnected different areas of study can be. Delving into gravitational interactions, dark photons present a fascinating prospect. They could decouple from electromagnetic forces under specific conditions, resulting in unique gravitational behaviors that merit further investigation. How might this decoupling influence our understanding of gravity? The implications are vast, suggesting that the fabric of space-time could be influenced by these interactions in ways we have yet to fully comprehend. The investigation of dark photons could also reveal intriguing connections to gravitational waves. Researchers are delving into the possibility that dark photons may influence the creation or detection of these ripples in space-time, especially in contexts involving massive celestial bodies like merging black holes or neutron stars. This intersection of fields enriches our comprehension of both dark matter and gravitational physics, highlighting how different areas of research can mutually enhance our understanding of the universe. Plasma filaments, the hidden highways connecting galaxies. Plasma filaments form the hidden highways of the universe, weaving through the vast cosmic landscape in ways that remain largely unnoticed. Imagine wandering through a city where the main roads are obscured by buildings and alleys. These filaments are much like those hidden paths, connecting galaxies in a dynamic network that influences the very fabric of the cosmos. It's essential to recognize their role in the grand cosmic design. These structures are not just voids of space, they serve as conduits for energy and matter, guiding the flow between galaxies. So, how do these filaments impact galaxy formation and evolution? They act as channels, funneling gas into galaxies, which is crucial for creating new stars. This makes them key players in the story of cosmic development. In exploring the origins of these filaments, we encounter baryon acoustic oscillations, sound waves from the early universe. These oscillations left their mark, creating the density fluctuations that formed the cosmic web we see today. But what's the connection between these sound waves and plasma filaments? The patterns established by these oscillations dictate where filaments will form, influencing their behavior and interactions with surrounding matter. Magnetic fields add another layer of complexity to our understanding of plasma filaments. These fields are prevalent throughout the universe, affecting how charged particles behave. Have you ever wondered how magnetic fields influence intergalactic matter? They play a vital role in regulating star formation rates, shaping the life cycle of stars and galaxies. Temperature variations within plasma filaments are equally significant. The gas can reach extreme temperatures, causing fluctuations that affect gas dynamics. Why does this matter? Such temperature changes can drive gas flows, stimulating star formation and leading to the emergence of vibrant stellar nurseries. This dynamic interplay is essential for understanding how galaxies evolve. The relationship between plasma filaments and dark matter is another captivating topic. How does this interaction enhance our grasp of dark matter's role in the universe? By studying how plasma filaments interact with dark matter, scientists gain insights into its distribution and influence, helping to unravel the mysteries surrounding this elusive substance. Astronomers utilize advanced radio telescopes and X-ray observations to analyze plasma filaments. What do these methods reveal about the universe? They provide detailed information about filament properties, enriching our understanding of cosmic dynamics. The influence of plasma filaments goes beyond mere connections. They shape the evolution of galaxies. Acting as a medium for material exchange, they impact how galaxies grow and develop over time. Why is this process significant? It affects the formation of galaxy clusters and influences our comprehension of the universe's evolutionary history. Computational simulations play a vital role in our exploration of plasma filaments. These models help predict how filaments will behave and interact over time. Why are simulations indispensable? They offer insights that observational data alone may overlook, allowing us to envision the intricate processes shaping cosmic structures. As galaxies traverse plasma filaments, they generate shock waves that affect their surroundings. What does this mean for the universe? These shock waves can heat nearby gas, altering the conditions for star formation and the thermal dynamics of clusters. Understanding these interactions is crucial for grasping the life cycle of galaxies. Plasma filaments also contribute to the phenomenon of gravitational lensing, where light from distant galaxies is bent. How does this effect benefit astronomers? By analyzing the distortion of light, researchers can map the mass distribution in the universe, enhancing our understanding of cosmic structures. In the context of cosmic reionization, plasma filaments might play a critical role. This period marked the transition of neutral hydrogen into ionized hydrogen, allowing light to travel freely. How do filaments facilitate this process? They could create conditions conducive to reionization, offering valuable insights into the early universe's environment. The Eridanus supervoid, the largest empty region in the known universe. The Eridanus supervoid is a fascinating cosmic anomaly that has captured the attention of astronomers and cosmologists alike. This immense region, larger than anything else we've observed, stretches across a staggering 1.8 billion light-years. To put that in perspective, that's about 6 times the diameter of our Milky Way galaxy. This vast emptiness raises significant questions about the nature of the universe and the distribution of matter within it. What does it mean for an area of space to be so devoid of galaxies and structures? One striking feature of the Eridanus supervoid is its lack of expected cosmic structures. It's not just a small gap in the cosmic web, it's a giant hole where one might expect to find galaxies clustering together. The void itself contains fewer galaxies than would typically be found in such a vast region. This raises an intriguing question. How did this massive void come to exist? Some scientists suggest that the supervoid may have formed through gravitational interactions, where matter was pulled away from the area over billions of years, leaving behind this emptiness. The Eridanus supervoid significantly influences our understanding of dark energy, a mysterious force that drives the accelerated expansion of the universe. This phenomenon interacts with matter in complex ways that scientists are just beginning to decipher. By observing how light from distant galaxies travels through this massive void, researchers can gain valuable insights into the nature of dark energy. These observations might help clarify how cosmic structures change over time and provide a deeper understanding of the universe's expansion dynamics. Additionally, the existence of the Eridanus supervoid presents intriguing challenges to current cosmological models. Many of these models have traditionally relied on the assumption that matter is distributed relatively uniformly throughout the universe. The discovery of such a vast void raises questions about these foundational assumptions. To account for the peculiarities associated with the Eridanus supervoid, cosmologists may need to adjust their simulations and theories. This process of refinement could lead to revolutionary insights into cosmic evolution, potentially reshaping our long-held beliefs about the universe's structure and behavior. Research into the Eridanus supervoid has uncovered that it is not completely devoid of galaxies. While the density of galaxies in this region is significantly lower than in neighboring areas, some faint, distant galaxies persist within this enormous void. These galaxies appear to have diminished star formation capabilities, suggesting they may evolve differently compared to their counterparts in denser environments. This observation prompts intriguing considerations about how galaxies adapt and change when situated in such expansive emptiness. Eridanus supervoid may have a surprising impact on the dynamics of galaxies in its vicinity. For instance, galaxies situated near the edges of this vast void could display unusual motion patterns that differ from those found in more densely populated areas. These unexpected movements might result from the gravitational influence of the supervoid, altering how matter and energy are distributed among nearby cosmic structures. As a result, understanding these interactions could shed light on the complex behavior of galaxies in low-density environments. By utilizing advanced radio telescopes and conducting extensive deep sky surveys, astronomers are gathering vital data on cosmic microwave background radiation as it interacts with the void. These efforts are illuminating the early universe and revealing how the supervoid has played a role in shaping cosmic evolution from its very beginnings. The gravitational influences of the Eridanus supervoid also present an area of great interest. Despite the scarcity of galaxies, the mass of the void still impacts surrounding regions through a process known as gravitational lensing. This effect bends the light from more distant galaxies as it passes near the supervoid, offering valuable insights into both the void itself and the celestial structures beyond. These lensing phenomena create opportunities to observe distant galaxies that would otherwise be hidden. Ancient megamasers, galactic lasers beaming from the distant past. Ancient megamasers, sending out powerful beams from billions of light-years away, offer a fascinating glimpse into the universe's history and evolution. Their emissions, often tied to distant galaxies, serve as beacons illuminating secrets about the cosmos, hidden for eons. The intriguing aspect of megamasers lies in their unusual molecular composition. They emit intense radio waves, primarily from molecules like hydroxyl, OH, water, H2O, and formaldehyde, H2CO. This specific composition is not merely a curiosity. It provides essential clues about the chemical evolution of galaxies. Imagine what revelations about the early universe could be contained in the beams of these ancient lasers. Looking deeper, we realize that megamasers are not just markers of cosmic time. They are time capsules. Observing their emissions allows us to peer back billions of years, offering insights into how galaxies formed and evolved. Each pulse carries information about the cosmos during its formative stages, begging the question, what can these megamasers tell us about the processes that shape the universe we know today? In many cases, megamasers are linked to starburst galaxies, regions where star formation occurs at an explosive rate. Understanding the connection between megamasers and these energetic environments can unveil the driving forces behind star formation and energy production. As we ponder this relationship, we might wonder, how do megamasers interact with their surroundings to influence the formation of new stars? Adding to their allure is the intriguing connection megamasers have with supermassive black holes. Many of these cosmic lasers are found near active galactic nuclei, hinting at a possible relationship between black holes and megamaser emissions. This influence of supermassive black holes on the surrounding molecular gas could explain how these powerful lasers are generated. What implications does this connection hold for our understanding of galaxy dynamics? Megamasers are like cosmic mile markers. They help us measure how far away galaxies are with amazing accuracy. This helps us understand how fast the universe is expanding and the forces that make it grow. It's like having a really precise ruler for the universe. Their emissions are incredibly consistent, making them valuable tools for astronomers calculating distances between galaxies. This precision plays a crucial role in refining our understanding of the universe's expansion, shedding light on the complex mechanics that govern cosmic growth. Among the various types of megamasers, OEH megamasers are particularly rare, often found in merging galaxies. Their presence offers key insights into how galaxy collisions create turbulence in molecular clouds, amplifying radio emissions. Delving into these rare phenomena raises questions about how such interactions shape the universe's large-scale structure. Now, what generates the extraordinary energy of a megamaser located over 1 billion light-years away? The intensity of these emissions far surpasses any we can create on Earth, prompting scientists to investigate the mechanisms behind such extreme energy production. Could these cosmic lasers hold the key to unlocking new understanding of the forces driving galaxy behavior? As we explore the natural symphony of megamasers, we discover their ability to be heard through their radio emissions. This unique quality allows astronomers to listen to the sounds of ancient galaxies, enriching our understanding of their internal processes. What fascinating stories might these cosmic sounds tell us about the evolution of the universe? Interestingly, many megamasers have been discovered serendipitously. Astronomers, while searching for different celestial phenomena, occasionally stumble upon these ultra-powerful water megamasers. This chance discovery prompts an intriguing thought. How many more colossal cosmic lasers lie hidden in the depths of space, just waiting for us to shift our focus? Megamasers also act as valuable clues regarding the distribution of dark matter. When light from distant galaxies passes through regions containing megamasers, scientists can study how gravity from unseen matter influences its journey. This interplay between visible and invisible mass offers indirect insights into the mysterious nature of dark matter, one of the universe's greatest enigmas. By analyzing the growth of megamaser activity over cosmic time, researchers can trace the evolving conditions within galaxies. This examination allows us to understand transitions between different epochs in cosmic history, particularly how galaxies have transformed over billions of years. What patterns emerge when we delve into these cosmic changes, and how do they shape our understanding of galactic evolution? Focusing on water megamasers, we discover their unmatched strength. Water molecules surrounding supermassive black holes create some of the most potent masers, generating beams so powerful they traverse millions of light-years. This invites a captivating question. Why are water masers so exceptionally powerful compared to other types of emissions? The presence of a megamaser often signals specific conditions within a galaxy. High turbulence or unusual radiation fields can lead to the formation of these remarkable emissions, acting as cosmic indicators of violent events occurring in distant galaxies. The Sun's mysterious corona. The Sun's corona is one of the most fascinating and perplexing features of our solar system. It radiates outward from the Sun's surface, extending millions of kilometers into space, yet it poses a significant mystery. Why is the corona so much hotter than the Sun's surface? While the surface temperature hovers around 5,500 degrees Celsius, the corona can reach staggering temperatures of up to 3 million degrees Celsius. This disparity has intrigued scientists for decades and suggests complex processes at work in the solar atmosphere. A leading hypothesis for the corona's extreme temperature centers on magnetic fields. The Sun's dynamic nature is characterized by complex magnetic activity evident in the loops and arches of the corona. These magnetic structures can accumulate energy, and when this energy is released suddenly, it heats the surrounding plasma. This process, known as magnetic reconnection, raises an intriguing question. Could this magnetic activity hold the key to unlocking the mystery of the corona's heating? Researchers are actively exploring the ways in which these magnetic fields shape the temperature and dynamics of the solar atmosphere. Turbulent motions occurring in the solar interior generate acoustic waves that travel upward into the corona. As these waves propagate, they can dissipate their energy in the corona, contributing to its elevated temperatures. Different types of waves, including sound waves and magnetohydrodynamic waves, are believed to interact with the solar atmosphere in varied ways. Understanding these interactions could provide valuable insights into the mechanisms behind corona heating. Researchers are actively exploring how these waves might influence the corona's temperature and behavior. A lot of people are interested in how the solar wind and the corona are connected. The solar wind is made up of charged particles that the Sun sends out into space. It has a lot of energy and speed, which can change the temperature of the corona. This exchange has an effect on more than just the corona. It also changes how the solar atmosphere moves in general. What role does the solar wind play in warming the corona? Studies show that the steady flow of solar wind is a key factor in making temps rise. This adds another level of complexity to the already complex situation. Observational missions like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe are vital for unraveling the mysteries of the corona. These advanced spacecraft are designed to study the solar atmosphere in unprecedented detail, collecting data that enhances our understanding of the corona's structure and behavior. As these missions continue their observations, they could unveil new findings that challenge our current understanding of the corona's heating mechanisms. What exciting discoveries might lie ahead as scientists analyze the wealth of data collected from these missions? Coronal mass ejections, CMEs, are another crucial factor in the dynamics of the corona. These massive bursts of solar wind and magnetic fields can release vast amounts of energy into the solar atmosphere, temporarily increasing the corona's temperature and altering its structure. When CMEs occur, they can create spectacular displays and significant changes in the corona's dynamics. How do these explosive events impact the temperature and behavior of the solar atmosphere? Understanding the relationship between CMEs and the corona is vital for grasping the complex nature of solar activity. The corona's dynamic nature adds an additional layer of complexity to our understanding. It is continuously changing due to solar activity, with features like coronal holes and streamers appearing and disappearing over time. These dynamic features not only contribute to the beauty of the corona, but also influence its heating and interactions with the solar system. How do these variations in the corona affect the overall dynamics of the solar atmosphere? As researchers study these changes, they gain insights into the mechanisms driving the corona's temperature fluctuations and energy distribution. Understanding the corona has significant implications for space weather, which can affect technology on Earth, including satellites and communication systems. As the corona influences solar activity, predicting these changes becomes crucial for safeguarding technological infrastructure. How can enhanced knowledge of the corona improve our ability to forecast space weather events? By deepening our understanding of the corona's behavior, scientists hope to develop better predictive models, ensuring that we are better prepared for solar storms and their potential impacts on our daily lives. The influence of the corona extends beyond our solar system, impacting the heliosphere, the bubble-like region of space dominated by the solar wind. The interaction between the corona and the heliosphere plays a crucial role in shaping the boundaries of this vast region, affecting cosmic rays and interstellar particles. How does the activity of the corona modulate conditions within the heliosphere? The dynamics of the corona can have a direct impact on the flux of cosmic rays entering our solar system, shaping the overall environment we experience. The study of the corona also presents exciting possibilities for future solar exploration. As scientists continue to uncover the intricacies of the corona, they may identify specific regions ripe for detailed investigation. What innovative technologies or missions might emerge to further our understanding of the solar atmosphere? Future missions may harness advanced imaging and sensing technologies, allowing us to probe the depths of the corona in ways previously thought impossible. Each discovery brings us closer to answering the profound questions surrounding this enigmatic layer of the Sun. Axions, the elusive particles that could explain dark matter. Axions represent one of the most tantalizing possibilities in modern physics, both in particle theory and cosmology. These elusive particles, if proven to exist, could fill a critical gap in our understanding of the universe, particularly regarding the elusive nature of dark matter. Though axions are challenging to detect, their potential influence on cosmic evolution and the formation of structures in the universe makes them central to unraveling the secrets of dark matter. First, mysteries surrounding axions are rooted in their theoretical origin. The strong CP problem, a fundamental puzzle in quantum chromodynamics (QCD), suggested that the strong force should violate the charge parity (CP) symmetry. Yet, observations show no such violation. To solve this discrepancy, physicists proposed axions in the 1970s, particles that would naturally explain why CP symmetry is preserved in the strong force. But the question remains, if axions solve this particle physics conundrum, how do they relate to dark matter, the substance that seemingly dictates the structure and fate of the cosmos? The duality of axions being proposed for both particle physics and cosmology makes them a unique key in understanding multiple unsolved mysteries. Dark matter itself remains one of the most pressing questions in cosmology. While it doesn't emit or absorb light, its gravitational effects are evident across the universe. Galaxies rotate faster than they should based on their visible mass, and galaxy clusters bend light in ways that require far more mass than what's observed. Could axions be the missing dark matter explaining these phenomena? Axions, being incredibly light and weakly interacting, fit the description. The gravitational behavior of dark matter could be accounted for by vast clouds of these particles, subtly shaping galaxies and the large-scale structure of the universe without ever being detected directly. A link between axions and astrophysics comes through white dwarf stars. These ancient, dim remnants of stars have been observed cooling faster than expected. Astrophysicists have speculated that axions could be carrying energy away from these stars, explaining the discrepancy. If axions can escape the dense core of a white dwarf, they might be playing a role in cooling stars across the universe. This connection between axions and stellar evolution adds another layer to the question. Are axions fundamental not only to the universe's structure, but to the very life cycles of stars? If true, this could radically alter our understanding of how stars evolve over billions of years. One of the most promising ways to detect axions directly is through their potential interaction with electromagnetic fields. This property opens the door to experiments like the Axion Dark Matter Experiment, ADMX, which aims to convert axions into detectable photons. Using strong magnetic fields, physicists hope to see these weakly interacting particles turn into visible light. The experiment is set up to detect axions within a specific range of masses, offering one of the few tangible methods to directly observe them. However, the challenge lies in the sheer elusiveness of these particles. While the ADMX experiment holds promise, the question arises: are we looking in the right place for axions, or could their properties lie just outside the detectable range? The early universe offers another clue in the hunt for axions. Theoretically, axions could have been produced in abundance during the first few moments after the Big Bang. If they existed, they would have influenced the formation of large-scale cosmic structures like galaxies and galaxy clusters. As the universe expanded and cooled, axions would have spread out and formed massive halos around galaxies, contributing to the gravitational effects attributed to dark matter. But if axions were present so early in cosmic history, how have they shaped the universe as we observe it today? This is where the cosmic microwave background radiation, CMB, comes into play. Any deviation in this ancient radiation left over from the Big Bang could potentially point to the influence of axions on the early cosmos. Neutron stars, among the densest objects in the universe, present yet another avenue for exploring axions. If these particles are created in the dense cores of neutron stars, they could escape and carry away energy, much like in white dwarf stars. The energy loss could affect how neutron stars evolve over time, potentially altering their observable properties. Detecting such an energy imbalance in neutron stars could offer indirect evidence of axions. Could neutron stars be quiet factories, producing axions, and silently releasing them into the universe? This idea opens up exciting possibilities for detecting axions in astrophysical environments, providing an alternative to laboratory-based experiments. Axions may also be tied to the axiverse theory, a concept emerging from string theory. In this framework, axions are just one of many light particles predicted to exist in a higher dimensional universe. If the axiverse is real, our universe could be filled with different kinds of axions, each with unique masses and properties. This would mean the search for axions isn't just about finding one particle, but potentially many different ones, each playing a role in cosmic evolution. Could the universe be far more populated with light particles than we ever imagined, shaping everything from galaxy formation to the expansion of space itself? The elusive nature of axions raises another question. Why haven't we detected them yet? Given the vast experimental efforts including ADMX, CAST and other searches for axions, why have we found no direct evidence? One reason may lie in the incredibly weak interactions of axions with normal matter. They are predicted to have such low mass and energy that they simply slip through our detectors unnoticed. Another possibility is that our current technological limitations prevent us from detecting them, meaning axions might lie just outside the sensitivity of today's instruments. Could advances in future technologies finally bring axions into view? Or are we missing a crucial piece of the puzzle in our theoretical understanding? Axions, a potential component of dark matter, could be hiding in plain sight. Their presence in galaxy clusters could subtly warp the way light from distant objects is bent, a phenomenon known as gravitational lensing. By carefully analyzing these lensing effects, astronomers might be able to indirectly detect axions and uncover a significant piece of the cosmic puzzle. One potential source of axions could be supermassive black holes. These cosmic behemoths might act as factories for axions, producing them as they spin. As axions are created, they could gradually slow down the black hole's rotation, leaving a subtle signature that astronomers might be able to detect. If these axions can escape the black hole's gravitational grip, they could be released into the universe, providing a new avenue for exploring dark matter. The Hubble constant discrepancy, a long-standing puzzle in cosmology, could be partially explained by the presence of axions. By influencing the amount of dark matter and energy in the universe, axions might subtly alter the expansion rate over time. As researchers continue to refine their measurements, axions remain a promising candidate for resolving this discrepancy and advancing our understanding of the universe's evolution. The first quasars, cosmic beacons from a time of chaos. Quasars are among the brightest and most enigmatic objects in the universe, and the first quasars, emerging just 1 billion years after the Big Bang, are especially intriguing. These ancient cosmic beacons tell a story of a universe in chaos, filled with turbulent forces that shape the galaxies we see today. The first quasars, powered by supermassive black holes at their core, provide a glimpse into the conditions of the early universe. As scientists continue to study these objects, we uncover more about the origin of galaxies, the reionization of the cosmos, and the mysterious growth of black holes in the universe's infancy. The most surprising aspect of the first quasars is their rapid formation shortly after the Big Bang. These early quasars formed during a period when the universe was still young and transitioning from a dense, opaque state into the transparent and structured cosmos we observe now. The rapid appearance of these colossal objects has puzzled astrophysicists, as it challenges existing models of black hole growth. Supermassive black holes require vast amounts of time and material to form, yet these early quasars reach staggering sizes in just a fraction of that time. Some scientists propose that these quasars may have formed through the direct collapse of massive gas clouds, skipping the intermediate stages of stellar evolution. This hypothesis could explain how such massive black holes existed when the universe was only 1 billion years old. At the heart of every quasar lies a supermassive black hole, and the first quasars were no exception. These black holes, often billions of times the mass of our Sun, devoured immense quantities of gas and dust from their surroundings, converting gravitational energy into light and releasing it across the universe. The early universe was rich in gas, and this abundance may have provided the fuel necessary for such rapid black hole growth. However, The conditions that allowed these black holes to form and grow so quickly are still poorly understood. The idea that the early universe had unique gravitational environments, perhaps more chaotic and efficient at funneling matter into black holes, remains an open area of investigation. These first quasars challenge our understanding of how black holes accumulate mass and whether different processes were at play in the universe's formative years. The role of quasars in the reionization of the universe is another critical piece of this puzzle. Following the Big Bang, the universe was filled with a dense, opaque fog of neutral hydrogen. Over time, light from the first stars and galaxies began to ionize this hydrogen, making the universe transparent. Quasars, with their intense ultraviolet radiation, were key players in this reionization process. Their powerful light was capable of breaking apart hydrogen atoms, allowing light to travel freely across the universe. Without quasars, the universe might have remained dark and opaque for much longer, delaying the formation of galaxies and stars. The exact contribution of quasars to reionization remains under investigation, but their role as cosmic lighthouses helped illuminate the universe in its earliest epochs. Quasars serve another important function in modern astrophysics. They are natural probes of the early universe. The light from the first quasars has traveled billions of years to reach us, and by analyzing this light, scientists can learn about the conditions of the universe during that time. These quasars act like cosmic time machines, allowing us to peer into the universe's distant past and observe how structures such as galaxies and clusters were forming. One of the key tools for this kind of study is the analysis of absorption lines in quasar spectra. As light from quasars passes through gas clouds, it is absorbed at specific wavelengths, providing a fingerprint of the chemical composition and temperature of the intervening gas. This method has revealed a great deal about the distribution of matter in the early universe and has helped map the large-scale structure of the cosmos. Despite their intense energy output, some of these quasars managed to persist for billions of years. This raises questions about how they sustained their fuel sources for such extended periods. In the dense, gas-rich environment of the early universe, it's possible that quasars were able to tap into vast reservoirs of material. Alternatively, some quasars may have had intermittent activity, turning on and off as they encountered new sources of fuel. This on and off behavior could explain how some quasars survived for such long periods, as they weren't constantly consuming material, but rather going through phases of intense activity, followed by quiet periods. The influence of quasars on the surrounding cosmic environment was profound. The first quasars ejected powerful winds and jets of particles that affected the galaxies around them. These winds were strong enough to blow gas out of galaxies, effectively quenching star formation in some cases. On the other hand, in certain regions, these quasar winds may have triggered the formation of new stars by compressing gas clouds and kick-starting star formation. This dual role, both inhibiting and encouraging star formation, makes quasars key players in the evolution of early galaxies. The precise impact of quasar winds on galaxy formation is still being explored, but it's clear that they had a profound effect on the cosmic landscape. The light from early quasars is often bent and magnified by the gravity of intervening galaxies in a process known as gravitational lensing. This effect allows astronomers to study both the quasars themselves and the galaxies that act as lenses. Gravitational lensing has revealed much about the distribution of dark matter in the universe, as the bending of light provides clues about the unseen mass in the intervening galaxies. In this way, quasars not only illuminate their surroundings, but also help map the invisible components of the universe, such as dark matter, that make up the majority of the universe's mass. The discovery of heavy elements in the spectra of early quasars has provided further insights into the history of the universe. Elements like carbon, nitrogen, and oxygen, which are produced in stars, have been found in the light from the first quasars. This suggests that by the time quasars formed, the universe had already gone through several rounds of star formation and supernova explosions, enriching the intergalactic medium with heavier elements. The presence of these elements in quasars indicates that the universe was already well on its way to forming complex structures like galaxies. This enrichment of the early universe with heavy elements points to a period of rapid and intense star formation that occurred before the first quasars ignited. Unlike stars, which have relatively stable brightness, quasars can flicker and change in brightness over short periods. This variability is thought to be caused by changes in the amount of material falling into the black hole at the center of the quasar. In the chaotic early universe, such fluctuations may have been even more pronounced, offering clues about the conditions in the regions surrounding these early quasars. Observing the flickering of quasars provides insights into the accretion process and how material is fed into supermassive black holes, shedding light on one of the most extreme environments in the universe. Experts who have looked into the first quasars have also found surprising things about time and space. Some scientists think that these things may be affected by strange physics, like the effects of extra dimensions or changes to how we understand gravity, because they have a lot of energy and are growing very quickly. Even though these are just ideas, they are being put to the test as we get more information from early quasars and look into what current cosmic models can't explain. Physicists and scientists are both very interested in the idea that quasars might hold secrets about the very nature of the universe. Exotic molecules in Titan's atmosphere. Titan, Saturn's largest moon, has long intrigued scientists due to its thick, nitrogen-rich atmosphere and vast methane lakes. One of the most fascinating aspects of Titan lies in the complex chemistry that occurs in its upper atmosphere, where the combination of solar radiation, cosmic rays, and unique molecules forms a chemical environment unlike any other in the solar system. Titan's atmosphere is thought to produce exotic organic compounds, including polycyclic aromatic hydrocarbons, PAHs, and cyanopolyeins, both of which have significant implications for prebiotic chemistry. These reactions suggest that Titan may be experiencing similar chemical processes to those that occurred on early Earth. However, what makes Titan even more remarkable is the discovery of molecules that are not typically found in planetary atmospheres, indicating that something extraordinary is happening above its surface. As scientists delve into the upper layers of Titan's atmosphere, they found unexpected forms of ionized molecules. These charged particles include large positively charged molecules that defy what we commonly observe in planetary atmospheres. Such ions could be key intermediaries, representing transitional forms between simple methane and larger organic compounds. It's possible that these ions are precursors to Titan's organic aerosols, the solid particles that give the Moon its distinctive orange haze. This type of chemistry, driven by ionization, is not just unique to Titan, but may be a critical process for forming complex organic matter throughout the cosmos. By analyzing these charged particles, researchers are uncovering a deeper understanding of how Titan's atmosphere might mirror early Earth's, especially regarding how organic compounds could eventually fall to the surface and contribute to its complex chemistry. Vinyl cyanide, a molecule with the potential to form structures similar to cell membranes in the Moon's methane lakes. What makes vinyl cyanide noteworthy is its ability to create membranes that are stable in liquid methane, as opposed to water. This raises fascinating possibilities about what life might look like in environments drastically different from Earth's. Recent models also indicate that Titan's atmosphere could contain other compounds that act as precursors to amino acids, the building blocks of life. These simulations lead to the tantalizing question: could Titan, with its extreme cold and lack of water, still support some form of life based on entirely different biochemical processes? While direct evidence remains elusive, the chemistry occurring in Titan's atmosphere points toward a moon that is rich with organic potential, possibly offering clues to how life may arise in conditions radically different from those on Earth. Titan's nitrogen atmosphere presents another enigma. The isotopic ratio of nitrogen, 14 to nitrogen 15 in Titan's atmosphere, is different from that on Earth or even the Sun. This unusual ratio has led scientists to question where Titan's nitrogen came from. Could the nitrogen have been delivered by comets after Saturn's formation? Or is it possible that Titan captured its nitrogen from the protoplanetary disk that formed the solar system? These questions point to the idea that Titan's atmosphere may have a more complex origin story than previously thought, with implications for how moons and planets develop atmospheres during their early histories. This nitrogen anomaly could be the key to unlocking not only Titan's past, but also how other moons and planets in the solar system acquired their atmospheres. Hydrogen cyanide, a simple but crucial molecule found on Titan, could be the key to the formation of more complex organic compounds. Scientists have shown in experiments that this molecule can link together to form long chains, similar to the building blocks of life on Earth. This raises the exciting possibility that Titan, despite its extreme conditions, could be a place where the first steps towards life are happening. In addition, Titan's frigid environment fosters unusual chemical reactions that challenge existing models. At temperatures plummeting to -290 degrees Fahrenheit, -179 degrees Celsius, reactions that typically occur only at much higher temperatures can proceed slowly, allowing for the formation of compounds like acrylonitrile and other exotic nitriles. These nitriles are rarely stable in warmer planetary atmospheres, yet on Titan they persist and even thrive. The discovery of such complex organic molecules in Titan's cold atmosphere suggests that our understanding of chemistry under extreme conditions may be limited. Researchers continue to explore the possibility that Titan's cold atmosphere serves as a natural laboratory for processes that are rare or impossible elsewhere in the solar system. While methane is the dominant gas in Titan's atmosphere, recent observations have found evidence of ethane clouds as well. These clouds are much rarer than their methane counterparts, but under certain conditions, ethane appears to condense and form rain, contributing to Titan's hydrocarbon lakes and rivers. The presence of ethane rain adds another layer of complexity to Titan's atmospheric cycle. It raises the possibility that Titan undergoes periodic changes in its atmospheric chemistry, driven by its slow seasonal shifts. Could there be ethane seasons on Titan, during which the moon's chemistry changes dramatically, similar to how seasons on Earth drive environmental shifts? The cycling of hydrocarbons between the atmosphere and surface provides a fascinating glimpse into how Titan's environment might fluctuate over time. The mysteries surrounding Titan are the origin of its thick orange haze, composed of organic aerosols. These aerosols form when methane and nitrogen in the atmosphere undergo photochemical reactions under the influence of sunlight and cosmic rays. Recently, scientists have discovered that these aerosols contain large hydrocarbon molecules that closely resemble tholins, compounds that may have played a significant role in the origin of life on Earth. Tholins are incredibly complex and form in large quantities in Titan's atmosphere, leading scientists to wonder if they could accumulate on the surface and play a role in the Moon's geological and chemical processes. While there's no direct evidence of life on Titan, the presence of tholins raises the intriguing possibility that similar compounds might have helped kickstart life on early Earth. Data from the Cassini spacecraft has been critical in uncovering new insights into Titan's atmosphere. One of the most surprising discoveries was the identification of exotic negatively charged molecules in the Moon's upper atmosphere, molecules that had never been seen in any other planetary atmosphere. These negatively charged particles are thought to be essential to the formation of Titan's organic hazes, as they can act as nucleation sites for larger organic structures. What's more, these findings have challenged existing models of atmospheric chemistry, suggesting that Titan's atmosphere may host processes entirely different from anything seen on Earth. By studying these unique ions, researchers hope to unravel more of Titan's mysteries and gain a deeper understanding of how organic molecules evolve in the harshest environments. The fascinating aspect of Titan's atmosphere is its potential to shed light on the early conditions of Earth. With its thick, methane-rich atmosphere and abundant organic molecules, Titan may offer a glimpse into what Earth looked like before life emerged. Could Titan be providing a natural laboratory for understanding the chemistry that led to life on our own planet? Tidal disruption events. Stars torn apart by supermassive black holes. The process of tidal disruption events, TDEs, presents a fascinating glimpse into the dynamics of our universe, particularly the interactions between stars and supermassive black holes. When a star ventures too close to a black hole, the immense gravitational forces begin to pull it apart. This phenomenon, known as spaghettification, leads to the stretching and ultimately the disintegration of the star. The resulting debris can create streams of material that may either be consumed by the black hole or remain in orbit around it. These TDEs serve as a crucial mechanism through which black holes can accumulate mass, especially in otherwise inactive galaxies. Once a star is disrupted, the material doesn't immediately disappear. Instead, some of it can form an accretion disk, a swirling mass of gas and dust spiraling towards the black hole. This so-called fallback material can linger around the black hole, leading to a sustained period of luminosity that may last from months to years. This temporal aspect of TDEs is essential because it can extend the observable impact of such events far beyond the initial disruption. But why do some TDEs produce more intense emissions than others? Research has indicated that the angle at which a star approaches a black hole can significantly influence the size and shape of the resulting accretion disk. The orientation of this disk can enhance the luminosity and consequently the observable light signatures of the event. In this sense, not only does the initial encounter matter, but the trajectory can dictate the fate of the stellar material and the energy it releases. One of the most astonishing phenomena associated with TDEs is the formation of relativistic jets. These high-energy jets can be ejected from the black hole's poles and are indicative of the intricate magnetic fields that can be present in such environments. The jets are typically observed in only a subset of tidal disruption events, suggesting that specific conditions must be met for their formation. Recent studies propose that the presence and configuration of magnetic fields surrounding the black hole are critical in determining whether jets will be produced. This raises intriguing questions about the relationship between magnetic activity and jet formation. Exploring the electromagnetic spectrum of TDEs reveals their multi-wavelength nature. From radio waves to gamma rays, these cosmic events illuminate a wide range of emissions. Interestingly, while optical and X-ray emissions often peak shortly after the star's disruption, radio emissions can have a delayed peak, sometimes appearing months later. This delayed response offers unique insights into how the black hole's environment evolves post-disruption. What causes this delay? It is theorized that the interaction of stellar debris with surrounding matter affects the timing and intensity of radio emissions, presenting an opportunity for researchers to study the interplay between matter and energy on a cosmic scale. The spin of supermassive black holes is notoriously challenging to measure. However, TDEs provide a rare opportunity for astronomers to estimate this crucial property. By analyzing the light curves produced during a TDE, scientists can infer the spin of the black hole, the manner in which a black hole interacts with the star, how it tears it apart, and how the debris behaves, offers clues about its rotational speed. Such measurements can help fill gaps in our understanding of black hole growth and evolution over cosmic time. The type of star undergoing disruption also plays a vital role in the characteristics of the resulting tidal disruption event. Different types of stars exhibit distinct behaviors during disruption. For instance, lower mass stars generate different light curves compared to massive stars. Interestingly, when white dwarfs are disrupted by intermediate mass black holes, the result is often a burst of X-rays rather than the optical flares typical of more massive stars. This raises a compelling question. How do the various stellar types contribute to the frequency of TDEs in different galaxies? One aspect of TDEs is the chemical signatures left in their emission spectra. When a star is torn apart, the debris can provide information about the star's original composition. For example, some TDEs have exhibited unusual quantities of nitrogen and oxygen, suggesting that the stars were rich in these elements. These chemical fingerprints offer an unparalleled opportunity to analyze the characteristics of stars that have long since been destroyed, providing insights into the conditions that existed in the galaxy prior to disruption. Moreover, the fate of the star's core after disruption remains a topic of considerable interest. While the outer layers are typically consumed by the black hole, some scenarios suggest that the core might survive in a highly compressed state. This surviving core could either be ejected from the vicinity of the black hole at high velocities or transform into a unique stellar remnant. Such remnants may help explain the presence of rogue stars, those traveling at unusual speeds across galaxies. Beyond the immediate impact on individual stars, tidal disruption events can have broader implications for their host galaxies. Although these events are relatively rare, the energy they release can trigger star formation in nearby gas clouds. This could potentially reignite dormant black holes, turning them into low-level active galactic nuclei. This unexpected ripple effect serves to illuminate why certain seemingly inactive galaxies exhibit bursts of activity without any apparent triggers. Tidal disruption events are not just cosmic spectacles. They are vital tools in our understanding of black hole behavior and the broader universe. The study of these phenomena helps elucidate the complexities of gravitational forces, magnetic activity, and the intricate interplay of various cosmic components. Each TDE offers a snapshot of an event that can help scientists unravel the mysteries surrounding black holes, stars, and galactic evolution. Invisible stars. Could our universe be filled with black dwarfs? Black dwarfs are fascinating cosmic concepts. They are stellar leftovers that, in principle, arise after white dwarfs cool down over billions of years. Their invisibility, in contrast to their brighter relatives, has piqued interest in these objects and their possible effects on the cosmos. We are discovering new facets of star development and cosmic dynamics as we delve into the intricacies of black dwarfs. The formation of black dwarfs begins with white dwarfs, which represent the final evolutionary stage for many stars. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers, leaving behind a dense core. This remnant, a white dwarf, is initially incredibly hot, glowing brightly as it radiates energy into space. However, over immense timescales, far exceeding the current age of the universe, these stars undergo a cooling process, gradually losing their heat and light until they become black dwarfs. The question arises, how long would this transition take? Estimates suggest that it could exceed 10 circumflex 15 years, a duration that far surpasses the time since the Big Bang. Currently, there are no confirmed observations of black dwarfs. This leads to the intriguing challenge of detection. How might astronomers identify these elusive stellar remnants? One proposed method involves gravitational microlensing, a technique that exploits the bending of light by massive objects. As light from distant stars passes near a potential black dwarf, it could reveal subtle distortions, offering a glimpse into these otherwise invisible stars. This quest not only highlights our limitations, but also our relentless drive to understand the universe's secrets. The cooling mechanisms of white dwarfs are complex and influenced by various factors, including mass and composition. Heavier white dwarfs cool more slowly due to their greater gravitational pressure, which affects how heat is distributed within the star. The transition from a bright white dwarf to a faint black dwarf encompasses a multitude of thermodynamics, illustrating the intricate interplay of physics governing stellar life cycles. A fascinating angle in the study of black dwarfs involves their potential connection to dark matter. Could these unseen objects contribute to the mysterious mass that seems to exert gravitational effects throughout the universe? If black dwarfs exist, they might account for some of the unseen mass influencing galaxy rotation curves. This connection challenges conventional views and invites us to reconsider what constitutes dark matter. The idea that invisible stars could form part of the universe's unseen fabric opens new avenues for research and speculation. As we ponder the implications of black dwarfs, we must consider their influence on galactic evolution. If these stellar remnants exist in significant numbers, they could alter the gravitational dynamics of galaxies. How would their presence reshape star formation rates and the distribution of mass? The existence of black dwarfs might lead to a redistribution of stellar populations, affecting the life cycle of galaxies and the processes that govern their growth and decay. This could provide crucial insights into the mechanisms driving the evolution of cosmic structures over time. In the broader context of stellar remnants, black dwarfs highlight the diversity of end states for stars, while neutron stars and black holes represent extreme outcomes of stellar evolution. Black dwarfs occupy a unique position in the spectrum of stellar remnants. Unlike neutron stars, which result from supernova explosions, or black holes formed from collapsing massive stars, black dwarfs emerge from a much slower and less violent process. This diversity underscores the complexity of stellar life cycles and invites comparisons with other forms of stellar evolution. The gravitational influence of these dark remnants could affect nearby stars and gas clouds, leading to a variety of outcomes. For instance, the gravity of a black dwarf might perturb the orbits of nearby stars, potentially causing changes in their trajectories. This gravitational interplay adds another layer to our understanding of how black dwarfs might impact the interstellar medium and the evolution of stellar populations in their vicinity. Inquiring into black dwarfs' possible consequences also makes us think about their wider effect on the cosmos. These objects may hold clues to the universe's ultimate destiny if studied properly. If black dwarfs represent a typical stellar demise, then knowledge of their characteristics and distributions might shed light on the cold death of the universe. When the vast majority of stars have used up their nuclear fuel and the universe has become dark and quiet. Furthermore, the theoretical existence of black dwarfs may intersect with concepts in quantum mechanics. At extremely low temperatures, matter behaves in ways that challenge our conventional understanding. Could black dwarfs reveal insights into quantum states of matter that remain elusive in current physics? Investigating their properties may uncover new phenomena related to quantum degeneracy and the behavior of matter in these unique conditions. This intersection of astrophysics and quantum theory opens exciting avenues for research and speculation. In connecting the existence of black dwarfs to other cosmic phenomena, we are reminded of the importance of persistence in scientific inquiry. Just as the study of tidal disruption events revealed new insights into the behavior of supermassive black holes, so too could the exploration of black dwarfs lead to unforeseen revelations about the nature of dark matter, galactic evolution, and the fate of the universe. The mysteries of the cosmos continually challenge our understanding, urging us to seek out the hidden wonders that lie beyond our current perceptions. The interplay between light and dark, between what we can observe and what remains hidden, paints a rich tapestry of cosmic evolution that we are only beginning to unravel. Galactic cannibalism, the Milky Way's history of devouring dwarf galaxies. The Milky Way galaxy, a majestic spiral of stars and cosmic dust, has a complex history that goes beyond what we can see with the naked eye. At the heart of its evolution lies a phenomenon known as galactic cannibalism. This term refers to the process where larger galaxies, like our Milky Way, consume smaller dwarf galaxies, reshaping their own structure and stellar population. Understanding this process sheds light on the dynamics that govern not just our galaxy, but others throughout the universe. Currently, the Milky Way is in the midst of absorbing several dwarf galaxies, with the Sagittarius dwarf spheroidal galaxy being the most notable example. This ongoing process provides an exciting glimpse into how galaxies evolve over time. What does this continual consumption tell us about the Milky Way's growth? It highlights the fact that galaxies are not static. They are dynamic entities, constantly interacting with and devouring their smaller counterparts. Diving deeper into this phenomenon reveals the significant role that dark matter plays in galactic interactions. Dwarf galaxies are often surrounded by halos of dark matter, which influence their gravitational interactions with larger galaxies. How does dark matter influence the dynamics of these interactions? It creates a gravitational framework that not only allows these dwarf galaxies to exist, but also facilitates their eventual merging into larger galaxies. As dwarf galaxies are consumed, they often leave behind stellar streams, elongated remnants of stars that were once part of the smaller galaxy. These streams serve as a historical record of the Milky Way's past interactions. For instance, what do these stellar streams reveal about the history of the Milky Way? They offer valuable insights into the galaxy's growth, frequency of past mergers, and the chemical evolution of the Milky Way itself. Each stream is a testament to the chaotic dance of galaxies, showcasing the remnants of a cosmic encounter. The chemical enrichment of the Milky Way is another critical aspect influenced by galactic cannibalism. When the Milky Way absorbs stars and gas from dwarf galaxies, it increases its metallicity, a crucial factor for star and planet formation. This process suggests that the stars we see today in the Milky Way have been shaped not only by their formation, but also by the ingestion of materials from once distant galaxies. As a result, the history of the Milky Way is interwoven with the stories of these smaller galaxies, making the study of dwarf galaxies essential for understanding our own cosmic identity. Moreover, recent observations using advanced telescopes have uncovered numerous streams and remnants of dwarf galaxies surrounding the Milky Way. This observational evidence reinforces the notion that galactic cannibalism is a fundamental aspect of galaxy evolution. As researchers sift through this data, they begin to map out the pathways of these consumed galaxies, piecing together a timeline of interactions that shaped the Milky Way. A phenomenon tied to galactic cannibalism is known as galactic harassment. This term describes the gravitational interactions that occur when smaller galaxies pass close to the Milky Way. These encounters can lead to the stripping away of stellar material, demonstrating the chaotic nature of galactic interactions. In such cases, the smaller galaxy is not merely consumed. It is torn apart, with its stars scattered across the Milky Way's gravitational field. While the consequences of galactic cannibalism are fascinating, they extend beyond the immediate vicinity of our galaxy. The mergers and interactions of dwarf galaxies may have left subtle imprints on the cosmic microwave background, CMB, the afterglow of the Big Bang. Researchers are investigating how the accumulation of mass from these cannibalized galaxies could have influenced the temperature fluctuations observed in the CMB. What does this suggest about the universe's early structure? It indicates that the history of galaxy interactions plays a crucial role in shaping the cosmos, revealing a deeper interconnectedness of celestial bodies. Another aspect of galactic cannibalism is its role in forming the Milky Way's halo. The halo is a vast diffuse region surrounding the galaxy, filled with dark matter and stars. As dwarf galaxies are absorbed, their remnants contribute to this halo, further complicating our understanding of galaxy structure. This process emphasizes how galactic cannibalism shapes not just the core of galaxies, but their extended structures as well. Traditional ideas of galaxy formation are still being challenged by research into these interactions. Galaxies are not solitary entities. They are part of a complex cosmic ecosystem that continuously interacts and evolves. This insight raises other questions. How frequently do such exchanges happen? And what elements influence the result of these encounters? The Milky Way's history of devouring dwarf galaxies is a story of growth and transformation. Each swallowed galaxy adds not just mass, but also diversity to the Milky Way's stellar population. The remnants of these encounters can be seen in the form of unique star clusters and streams that trace the history of galactic interactions. Galaxies without dark matter. The case of NGC 1052 DF2. NGC 1052 DF2 is an unusual galaxy that has captured the attention of astronomers around the globe. Discovered through the Dragonfly telephoto array, the galaxy stands out not just because of its faintness or size, but due to its apparent lack of dark matter, a feature thought to be a fundamental component of galaxies. Follow-up observations from the Hubble Space Telescope and the Keck Observatory provided the shocking confirmation that NGC 1052 DF2 behaves contrary to our understanding of galactic physics. Typically, galaxies are understood to be tightly bound by dark matter halos, invisible gravitational forces holding together the vast masses of stars and gas. However, when observing NGC 1052 DF2, astronomers noticed something peculiar. The stars within the galaxy were moving at speeds far slower than would be expected if dark matter were present. Without this invisible glue, the galaxy shouldn't behave in the same way as those dominated by dark matter. This discovery raises a troubling question. How can a galaxy, devoid of dark matter, even exist? One leading theory suggests that NGC 1052 DF2 may have once had dark matter, but was stripped of it during an interaction with a nearby massive elliptical galaxy, NGC 1052. Tidal forces from NGC 1052 could have torn away the dark matter halo, leaving only the visible matter behind. This type of interaction, known as tidal stripping, has been observed in other cases and offers one possible explanation for the galaxy's current state. But even if tidal stripping played a role, this galaxy remains a puzzle in more ways than one. Its structure is far more diffuse than most galaxies of its size, with stars spread across a vast region of space, rather than clustering tightly, as they would in a dark matter-rich galaxy. The gravitational pull that would normally condense and cluster these stars is notably absent, suggesting that without dark matter to rein them in, the stars are free to roam across larger distances. An interesting side note to NGC 1052 DF2's story is its population of globular clusters, spherical collections of stars that orbit galaxies. What makes these globular clusters so intriguing is their slow movement. Typically, globular clusters are fast-moving entities held in the gravitational grip of a galaxy's dark matter halo. Yet, around NGC 1052 DF2, these clusters appear to be moving sluggishly. This further reinforces the idea that the galaxy is devoid of dark matter. With no substantial mass to pull them, the globular clusters float at a slower pace. There is also the possibility that NGC 1052 DF2 never had dark matter in the first place. This brings us to one of the more controversial discussions in modern astrophysics. Is dark matter truly necessary for the formation of galaxies? Could NGC 1052 DF2 be an example of an alternate process by which galaxies can form without dark matter? The majority of current models assume that dark matter is essential for the formation and stability of galaxies. However, if NGC 1052 DF2 is the product of an alternative mechanism, it could force astronomers to rethink the role of dark matter in galactic evolution. A potential alternative explanation is modified Newtonian dynamics, MOND. MOND suggests that gravity behaves differently in low acceleration environments, such as the outer reaches of galaxies. In these conditions, gravity alone could account for the dynamics of stellar movements without invoking dark matter. Although this theory has not gained widespread acceptance, NGC 1052 DF2's peculiarities provide intriguing data points that challenge the dominance of the dark matter paradigm. More recently, NGC 1052 DF2's status as a cosmic outlier has been challenged by the discovery of a second galaxy, NGC 1052 DF4, which also appears to lack dark matter. This raises the tantalizing possibility that there may be many more galaxies like these, hidden in plain sight, waiting to be discovered. If multiple galaxies can exist without dark matter, it suggests that our current cosmological models might be incomplete. Could NGC 1052-DF2 and its twin, NGC 1052-DF4, represent just the tip of the iceberg when it comes to understanding the diversity of galactic forms? One of the major implications of these discoveries is the potential shakeup of cosmological models like the lambda cold dark matter (LCDM) model, which relies heavily on the existence of dark matter to explain the large-scale structure of the universe. If galaxies can exist without dark matter, and if there are many more of them out there, it could mean that dark matter isn't as ubiquitous or as crucial to galaxy formation as previously thought. However, such a conclusion would demand a rethinking of many core ideas in modern cosmology. Aside from theoretical implications, the proximity of NGC 1052-DF2 to its larger neighbor, NGC 1052, raises practical questions about how galaxies interact with one another. Could tidal forces from larger galaxies be stripping smaller galaxies of their dark matter on a regular basis? While this idea has gained some traction, there's still much to be learned about how gravitational interactions between galaxies play out over time. In fact, recent observations have shown that not all galaxies retain their dark matter when placed near a massive companion. It's plausible that galaxies like NGC 1052-DF2 are more common in environments with large gravitational forces, such as galaxy clusters. If true, the study of NGC 1052-DF2 and galaxies like it could yield new insights into the complex gravitational interactions within galaxy clusters and how they influence the development of their constituent members. Could this galaxy be the result of a rare cosmic event that stripped away its dark matter? Or is it an example of a class of galaxies that follow a different evolutionary path altogether? Recent advancements in astronomical technology, such as the use of advanced spectrographs and more sensitive telescopes, will allow researchers to gather more data to solve these mysteries. Additionally, as computational models of galaxy formation become more sophisticated, astronomers will be able to simulate conditions under which galaxies like NGC 1052-DF2 could form, with or without dark matter. It's worth noting that while the galaxy's lack of dark matter is its most striking feature, NGC 1052-DF2 also provides new insights into the behavior of visible matter in extreme conditions. The diffuse star distribution and the slow-moving globular clusters paint a picture of a galaxy that operates on different rules than most others. These unique features offer researchers an unprecedented opportunity to study how stars behave in the absence of dark matter's influence. Ultimately, the ongoing research into NGC 1052-DF2 challenges some of our most fundamental assumptions about how galaxies form and evolve. While dark matter is still considered a key player in the universe's structure, NGC 1052-DF2 reminds us that the cosmos is filled with exceptions to every rule. The missing baryon problem. Where is most of the universe's normal matter? Baryonic matter makes up the stars, planets, and even us, everything we can physically observe. Yet, curiously, our understanding of this fundamental component of the universe is incomplete. The missing baryon problem is one of cosmology's enduring puzzles, leaving us asking, where is the rest of the universe's normal matter? The cosmic microwave background, CMB, the remnant radiation from the Big Bang, reveals much about the early universe. Precision measurements from satellites like WMAP and Planck have shown that baryonic matter should make up roughly 5% of the universe's total energy density. This number, while relatively small compared to the 25% attributed to dark matter or the 70% to dark energy, is what gives us the material cosmos we observe. Yet, when we tally up all the stars, galaxies, and interstellar gas, we only account for about half of this predicted baryonic content. Where is the rest? One promising lead comes from the study of the warm-hot intergalactic medium, WIM, a diffuse hot gas believed to be spread throughout the cosmos, filling the spaces between galaxies. Temperatures in the WIM can reach millions of degrees, making it virtually invisible to optical telescopes. However, its existence can be inferred through X-ray emissions and the absorption of light from distant objects, like quasars. Quasars, those ancient beacons from a chaotic time in the early universe, serve as invaluable tools for studying the intervening gas. The faint imprints they leave behind can tell us about the material that lies between us and these distant objects, providing indirect evidence of the missing baryons hiding in plain sight. The intergalactic medium, specifically WIM, may contain a large fraction of the baryons that have eluded detection for so long. Scientists estimate that WIM could account for anywhere from 30% to 50% of the missing baryons, based on indirect signals observed in X-ray spectra. But as with many cosmic puzzles, the story is far from straightforward. One might ask, how can we be sure that this hot, diffuse gas contains the baryons we're looking for? The answer lies in future improvements in X-ray spectroscopy and radio astronomy, both of which will offer more precise measurements of the absorption and emission lines from these gases. Beyond WIM, quasar absorption lines provide another clue. As light from these distant objects passes through gas clouds between galaxies, certain wavelengths are absorbed, creating a unique fingerprint. These absorption lines, particularly of ionized oxygen, OVI, offer a way to measure the density and distribution of intergalactic baryons. This method has allowed researchers to track baryons along cosmic filaments, long threads of matter that stretch across the universe, connecting galaxies like a vast cosmic web. Cosmic web itself may be the key to understanding the missing baryons. Cosmological simulations show that after the Big Bang, matter didn't just form galaxies and stars, but also vast networks of filaments, with clusters of galaxies at the intersections. These filaments are thought to house much of the universe's gas that could be the missing baryons we're searching for. The difficulty lies in detecting these faint structures. While they don't emit much light themselves, recent advancements in radio astronomy and precision instruments, like the Square Kilometre Array, SKA, are providing glimpses into these hidden structures. This brings us to the intriguing question: could the majority of the universe's baryonic matter be hiding in the cosmic web? If so, the very structure of the universe may hold answers to one of cosmology's most persistent mysteries. As new data is collected, the delicate filaments that connect galaxies could yield more clues about the missing matter. Fast radio bursts, FRBs, very brief but powerful radio wave bursts, offer even another exciting path for baryon discovery. First found in 2007, FRBs were enigmatic until scientists found their signals were delayed when they traversed the intergalactic medium. These delays, also known as dispersion measures, show how much ionized gas the radio waves came over, providing even another indirect means of finding missing baryons. By means of increasing data on FRBs, researchers expect to better grasp the baryon count and distribution in the universe. Galaxy clusters and superclusters provide another reservoir for baryonic matter. These massive structures contain not only galaxies, but also vast amounts of hot gas. X-ray observations from telescopes like Chandra and XMM Newton have detected significant amounts of this gas, contributing to the baryon census. Yet even here, there's a catch. The amount of gas detected still doesn't fully account for the missing baryons. It's possible that even hotter, more diffuse gas exists in these clusters, awaiting discovery by the next generation of telescopes. Turning to individual galaxies, the baryon discrepancy takes a more nuanced form. Consider dwarf galaxies, the faint, low-mass companions to larger galaxies like the Milky Way. Recent studies suggest that these galaxies may hold more baryonic matter than we initially thought, particularly in the form of neutral hydrogen gas. Dwarf galaxies are often neglected in large surveys due to their faintness, but they might contribute significantly to the missing baryon puzzle. Moreover, Their role in galaxy formation and cosmic evolution may be more critical than previously realized. We also look at a more peculiar candidate, ultra-diffuse galaxies, UDGs. These large but faint galaxies challenge our understanding of baryonic matter distribution. Some UDGs contain very little dark matter, which is unusual given their size, while others appear to have a significant gas component. Could these ghostly galaxies be reservoirs of the missing baryons? Recent findings suggest that UDGs may contain enough baryonic matter to tip the scales, but the evidence remains sparse. Lastly, cosmic voids, the enormous empty regions between galaxy clusters, present a tantalizing possibility. These voids, while nearly devoid of stars and galaxies, might contain a thin soup of ionized gas. Some estimates suggest that voids could house a significant fraction of the missing baryons, although direct observations are challenging. The detection of faint emissions from voids using sophisticated spectroscopic techniques is slowly building a case for their contribution to the baryon content of the universe. The deeper we dig, the more complicated things we find. We are getting closer to putting together the full list of baryons with each new finding. These include intergalactic strands, the cosmic web, fast radio bursts, and ultra-diffuse galaxies. But, just like with dark matter and dark energy, the missing baryons make us face a world that keeps most of its secrets hidden. Quantum foam, the bizarre structure of space-time at the smallest scale. Quantum foam, a concept proposed by physicist John Wheeler in 1955, depicts space-time at its smallest scale, far from the smooth fabric of Einstein's general relativity. At this Planck scale level, reality becomes a frothy sea of space-time fluctuations where quantum effects dominate and classical physics fades into chaos. But what does it mean for the universe we experience, and how does this invisible, turbulent landscape fit into our broader understanding of reality? Quantum foam is tied to the smallest possible unit of length, the Planck scale, measured at 1.6 x 10 circumflex 35 meters. This scale represents a realm where the distinction between time and space begins to dissolve, with both behaving in ways completely foreign to human intuition. It is here that the seemingly solid ground of space-time becomes an unpredictable maelstrom. At this scale, general relativity and quantum mechanics, the two most successful theories in physics, clash, with their principles conflicting dramatically. The fine structure of space-time is no longer stable, a bizarre foundation to the reality we know. This chaotic substructure of space-time holds not only scientific fascination, but hints at mysteries still unsolved. We know the universe on large scales follows certain rules, like gravity shaping the motion of stars and galaxies. However, quantum foam suggests that at the tiniest scale, these rules are upended. The nature of space-time itself becomes subject to Heisenberg's uncertainty principle, meaning that the precise position and momentum of space-time cannot both be known. Space and time bubble with uncertainty, and these fluctuations result in the birth of virtual particles, particles that pop in and out of existence, borrowing energy from the quantum vacuum. Could the properties of quantum foam be connected to other puzzling aspects of the universe, like the fast radio bursts, FRBs, that seem to carry enormous amounts of energy in fleeting moments? The quantum instability in space-time might generate events that leave faint echoes in high-energy phenomena like FRBs. Although FRBs occur on vastly different scales than quantum foam, exploring the chaotic origins of space at its smallest dimension might hold clues to understanding these bursts. When discussing quantum foam, one of the most compelling avenues of exploration is its role in quantum gravity. At present, quantum foam is often thought of as one possible key to unifying quantum mechanics and general relativity into a single coherent theory, a quest known as quantum gravity. String theory is one of the most promising contenders for this unification. In string theory, all particles are replaced by tiny vibrating strings, and space-time itself is made up of these strings interacting with one another at the Planck scale. The chaotic energy that quantum foam embodies could underpin these strings, providing the scaffold on which space-time, matter and energy emerge. Yet, despite being a theoretical framework for now, some researchers wonder if quantum foam could ever be detected or observed. The effects of quantum foam may ripple across space-time in subtle ways. For instance, it has been speculated that quantum foam could introduce faint distortions in the light traveling to us from distant objects like quasars. When the light from these ancient cosmic beacons crosses through the foam, it might pick up tiny fluctuations, though detecting such minute effects remains a formidable challenge. Can modern gravitational wave detectors, like LIGO or Virgo, eventually find evidence of these quantum fluctuations within the data? Stephen Hawking's discovery of Hawking radiation, that black holes emit small amounts of radiation over time, suggests that quantum foam could be active around the event horizons of black holes. At the event horizon, the boundary beyond which nothing can escape a black hole's gravitational grip, quantum effects cause the creation of virtual particles. In a phenomenon related to quantum foam, one of these particles falls into the black hole, while the other escapes, contributing to the slow evaporation of black holes over time. The chaotic nature of quantum foam may provide the perfect environment for this process to unfold. Taking a broader cosmic view, quantum foam may have shaped the early universe. The inflationary period, a moment of rapid expansion after the Big Bang, could have been influenced by quantum fluctuations in space-time. These fluctuations, caused by quantum foam, might have laid the groundwork for the distribution of matter in the universe we see today. This echoes how dark matter, another invisible and enigmatic force, shapes the galaxies and cosmic structures around us. If dark matter sculpts the universe at large scales, quantum foam may do so at the tiniest ones. Speaking of invisible forces, could quantum foam be tied to dark energy, the mysterious force causing the universe to expand at an accelerating rate? Dark energy remains one of the greatest mysteries in cosmology, responsible for roughly 68% of the universe's total energy content. Though quantum foam operates at the smallest scales, its cumulative effects over cosmic distances might contribute to dark energy. A fascinating idea is that the constant bubbling of space-time could create a residual energy field that exerts pressure, pushing galaxies apart. Another unusual manifestation of quantum foam could be the Casimir effect, a phenomenon observed in laboratory settings. In this effect, two uncharged plates placed close together experience an attractive force due to quantum fluctuations between them. The space between the plates, while appearing empty, is teeming with activity at the quantum level, a direct consequence of the underlying quantum foam. While the Casimir effect is a small-scale laboratory observation, it demonstrates how the vacuum of space is not as empty as once thought. Instead, quantum foam fills it with a hidden energy structure, subtly influencing physical objects. One of the most thought-provoking questions about quantum foam is how it may affect time itself. At the quantum level, time may no longer be a continuous smooth flow. Instead, some experts propose that time is an emergent property, a phenomenon arising from quantum entanglement and interactions within quantum foam. If true, this would suggest that the linear passage of time is merely a macroscopic illusion, and at the smallest scales, time is tangled and chaotic. Could the chaotic structure of quantum foam imply that time, like space, is not a fundamental aspect of reality? In this view, time might break down at the Planck scale, where quantum space-time fluctuates in ways that defy our everyday experience. The implications of quantum foam also extend to our understanding of the vacuum of space. Far from being empty, the vacuum at the quantum level is brimming with activity, virtual particles, energy fluctuations, and space-time distortions. This is where the boundary between something and nothing begins to blur. The energy density of quantum foam might even hold answers to another long-standing cosmological question: the fate of the universe. The energy contained within quantum fluctuations could affect the overall curvature of space, influencing whether the universe will continue expanding forever, collapse back in on itself, or reach some stable equilibrium. Quantum foam represents one of the final frontiers in theoretical physics, a frontier where space-time, matter, and energy merge into a chaotic froth of uncertainty. It challenges us to reconsider the nature of reality itself, where our most familiar concepts, like space and time, may be revealed as temporary conveniences rather than eternal truths. Whether through quantum gravity, dark energy, or the structure of the early universe, quantum foam is deeply connected to the most profound questions in cosmology. Fermi bubbles, peculiar gamma-ray bubbles. Fermi bubbles, vast structures radiating gamma rays, are one of the most compelling mysteries of our galaxy, the Milky Way. Discovered by NASA's Fermi Gamma-Ray Space Telescope in 2010, these bubbles extend an astonishing 25,000 light-years above and below the galactic center, raising questions about their origins and implications for cosmic evolution. The Fermi bubbles are not just random occurrences, they are intricately linked to the galactic dynamics of the Milky Way. They possess a unique shape and energy profile that challenge existing theories of how galaxies evolve and emit energy. Their gamma-ray emissions, highly energetic and unexplained by conventional galactic processes, prompt researchers to explore the possibility that these structures might be remnants of an ancient active galactic nucleus phase. In a world where scientific inquiry pushes the boundaries of what we know, the origins of these enigmatic bubbles remain hotly debated. Two leading theories seek to explain their existence: a surge of energy from the supermassive black hole Sagittarius A*, located at the Milky Way's core, or a period of intense star formation known as a starburst. The presence of these bubbles raises an intriguing question. Could they represent the remnants of the Milky Way's active galactic past, akin to those observed in distant quasars? As researchers delve deeper into the physics of the Fermi bubbles, they discover a crucial component: cosmic rays. The bubbles are filled with highly energetic particles that suggest an ongoing acceleration process. This revelation leads to a pivotal inquiry about the mechanisms involved in accelerating cosmic rays to near-light speeds. Could magnetic fields within the bubbles serve as a cosmic accelerator? This hypothesis remains unverified, leaving the question of how such extreme energies are produced an open topic of discussion in astrophysics. Furthermore, the Fermi bubbles have consequences outside the Milky Way as well, as comparable gamma-ray lobes have been found in other galaxies, according to current research. All of this points to the possibility that the Fermi bubble events are not unique to our galaxy. They may, instead, stand for something universal, proof of the commonalities in the history of galaxy evolution. The discovery of gamma-ray lobes in other galaxies opens the door to a more comprehensive study of cosmic structures and the distributions of their energies. Dark matter, an elusive yet crucial component of our universe, also finds its place in the discussion surrounding the Fermi bubbles. Some scientists speculate that dark matter interactions could explain the high-energy gamma rays observed in these structures. This raises fundamental questions. Could the bubbles serve as indirect evidence for dark matter annihilation? The interplay between dark matter and visible matter in these regions adds layers of complexity to our understanding of the universe. Estimating the age of the Fermi bubbles is an issue that arises when we think about the cosmic timescales that were involved in their development. Is the Milky Way's continuous development responsible for these more recent formations, or are they cosmic artifacts dating back millions of years? Astronomers use a variety of methods, including determining the sizes and velocities of particles inside the bubbles, to try to answer this question. The data are still not certain, though, so we can only speculate on the lifespans of cosmic structures. The relationship between the Fermi bubbles and galactic winds also warrants attention. Galactic winds, which comprise gas and dust expelled from the Milky Way's core, may influence the formation and maintenance of these bubbles. The interplay between these outflows and the bubbles could be vital in understanding energy transfer processes in the galaxy. It raises another essential question. How do these galactic winds shape the energy distribution in the bubbles? And what does this mean for the Milky Way's evolution? An intriguing aspect of the Fermi bubbles is their potential impact on the Milky Way's magnetic field. Researchers believe that these bubbles may interact with and shape the magnetic environment of our galaxy. The consequences of such interactions might extend beyond the bubbles themselves, influencing cosmic ray propagation and energy flows across vast distances. This connection highlights the need for further investigation into how large-scale magnetic fields affect galactic evolution and what insights the bubbles can provide regarding the Milky Way's magnetic characteristics. Significance of the Fermi bubbles stretches into the realm of astrobiology. By studying these high-energy environments, researchers can glean insights into the conditions that may or may not support life elsewhere in the universe. This inquiry leads to a fascinating consideration. How might the gamma-ray emissions from these bubbles impact the habitability of surrounding regions? The extreme conditions associated with high-energy environments pose potential challenges for the formation and sustainability of ecosystems in nearby stellar. The Oort cloud's secrets. Could life's origins be hidden on its icy bodies? The Oort cloud, often considered a distant frontier of our solar system, remains shrouded in mystery and intrigue. This vast region, believed to harbor a myriad of icy bodies, offers tantalizing possibilities regarding the origins of life and the building blocks necessary for its emergence. Comprising remnants from the solar system's formation, the Oort cloud could hold the keys to understanding not only our own history, but also the broader question of life beyond Earth. The formation of the Oort cloud is a fascinating tale that dates back approximately 4.6 billion years. As the solar system coalesced from a swirling disk of gas and dust, the gravity of the young sun helped to shape the dynamics of this primordial material. While the inner solar system formed rocky planets, the outer regions were left with icy bodies, which later coalesced to create the Oort cloud. This cloud acts as a reservoir of ancient material, encapsulating clues about the early solar system and the processes that led to the formation of planets, moons, and potentially life itself. Diving deeper into the composition of the Oort cloud, scientists have posited that its icy bodies are rich in water ice, ammonia, methane, and other volatile compounds. This composition is critical, as it mirrors the building blocks of comets, which have been suggested to be potential carriers of life's essential ingredients. The icy bodies within the Oort cloud may serve as time capsules, preserving the organic molecules that could have played a significant role in the emergence of life on Earth and possibly elsewhere in the universe. The means of movement for these frozen objects is central to an enticing idea about the Oort cloud. Here, the huge planets' gravitational pulls, especially Jupiter's and Saturn's, are crucial. Objects in the Oort cloud may have their orbits disturbed by these large things, which might cause them to move closer to the inner solar system. Planets in this domain are vulnerable to collisions with extraterrestrial objects, which might disperse the building blocks of life onto Earth. The complex interplay of planetary masses has us wondering how the circumstances for life would have been set up, and it has us marveling at the interdependence of the universe. Investigating the effects of these frozen objects on Earth is one of the most exciting areas of study. Crucial elements and compounds might have been delivered to early Earth by comets from the Oort cloud that collided with the planet. The amount to which these events affected Earth's water supply and organic chemistry is one example of an issue that scientists have argued over for quite some time. Might the circumstances for life to thrive have been ignited by these cosmic collisions? Researchers are still trying to figure out what these consequences meant and how they revealed the cosmic environment's direct influence on Earth's biological processes. Beyond the classical view of the Oort cloud as merely a source of icy bodies, recent findings suggest that some of these objects might exhibit cryovolcanism. This phenomenon occurs when internal heat drives the ejection of material from beneath the icy crust, similar to volcanic activity on Earth. If such cryovolcanic activity exists, it could create subsurface oceans that provide environments potentially suitable for microbial life. The implications of this discovery are profound. Rather than limiting the search for extraterrestrial life to planets and moons within the inner solar system, scientists must also consider the icy bodies lurking in the Oort cloud. In astrobiology, the age and stability of the Oort cloud present intriguing insights into the history of the solar system. Estimates suggest that the Oort cloud has remained stable for billions of years, preserving its icy inhabitants in a relatively unchanged state. This stability allows scientists to study the ancient history of our solar system and gain insight into the conditions that may have supported life in its infancy. By examining these long-lived objects, researchers can piece together a narrative of the universe that stretches back to its earliest moments. To unravel the mysteries of the Oort cloud involves ongoing cometary surveys and the discoveries that arise from them. As astronomers continue to study comets, they gather invaluable data regarding the composition and dynamics of Oort cloud objects. The knowledge gained from these studies not only enriches our understanding of the Oort cloud itself, but also sheds light on the potential for life-supporting compounds to be delivered to inner solar system bodies. Such discoveries could have far-reaching implications for our understanding of the universe and the origins of life. As experts investigate the processes that may have led to life on Earth, they must consider the contributions of the Oort cloud and its icy bodies. The idea that organic compounds, essential for life, may have originated from these distant realms expands the possibilities for life beyond our planet. The search for extraterrestrial life takes on new dimensions as researchers begin to understand the interconnectedness of cosmic events and biological processes. The influence of stellar encounters on the Oort cloud adds yet another layer of complexity to our understanding of this enigmatic region. When nearby stars pass through the Oort cloud, their gravitational forces can disrupt the delicate balance of its objects, sending some tumbling toward the inner solar system. This interaction raises fascinating questions about the frequency of such events and their potential impact on life's origins. The axis of evil, a cosmic alignment that shouldn't exist. The axis of evil presents an enigmatic phenomenon within the realm of cosmology, challenging our conventional understanding of the universe. This intriguing alignment refers to peculiar patterns observed in the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. At first glance, the CMB should exhibit uniformity, a feature anticipated by the standard model of cosmology. Yet, the axis of evil introduces an unexpected twist, as large-scale structures exhibit a distinctive orientation, suggesting the universe might not be as isotropic as once thought. The CMB anomalies pose profound questions about the very fabric of the universe. Researchers have dedicated significant effort to understanding whether these alignments could arise from intrinsic cosmic properties or if they stem from external influences. The likelihood of such alignments occurring by chance is exceedingly low, as statistical analyses indicate deviations from the predictions based on our current cosmological models. This intriguing divergence invites scientists to reconsider the underlying principles of cosmology and what they might reveal about our universe's evolution. Local cosmic structures, particularly the Milky Way and its surrounding galaxies, may influence the CMB measurements. This potential interaction raises questions about the extent to which our galactic environment could distort the signals we receive from the far reaches of the cosmos. Such influences highlight the interconnectedness of cosmic phenomena and underscore the importance of understanding our position within the universe when interpreting cosmic data. They may hold valuable insights into dark energy, the mysterious force driving the accelerated expansion of the universe. If the universe's isotropy is called into question, it could lead to revisions of the cosmological constant, fundamentally altering our comprehension of dark energy's role. These new models may not only clarify our understanding of the universe's expansion, but also reshape the way we conceptualize the forces that govern cosmic dynamics. The axis of evil has also prompted discussions about high-energy physics and the contributions of facilities like the Large Hadron Collider, LHC. Findings from the LHC may provide crucial insights that bridge the gap between particle physics and cosmology. If certain particle interactions observed at the LHC correlate with the anomalies seen in the CMB, it could offer new pathways to understanding the cosmos's behavior at its most fundamental level. The idea that the Milky Way's rotation could relate to the alignment of the CMB is a fascinating prospect. If our galaxy's motion influences cosmic patterns, it could imply that the Milky Way is not merely a participant in the cosmic dance, but rather a pivotal player in shaping the universe's structure. This notion of galactic influence highlights the interconnectedness of cosmic phenomena and challenges us to reconsider our assumptions about the hierarchical structure of the universe. Looking ahead, the advent of next-generation telescopes, including the James Webb Space Telescope, promises to revolutionize our understanding of the universe. With high-resolution observations on the horizon, these instruments may unravel the complexities surrounding the axis of evil. Enhanced data could help differentiate between competing theories of cosmic structure formation, offering new perspectives on the anomalies we observe. The intersection of quantum mechanics and cosmology introduces another layer of complexity to the axis of evil. Some physicists propose that quantum fluctuations in the early universe could explain the observed alignment. This convergence of disciplines encourages innovative thinking and a re-evaluation of how we understand the universe's structure. The prospect of integrating quantum mechanics with cosmological observations may lead to groundbreaking revelations about the fundamental nature of reality. The effects for galaxy distributions and dark matter are being debated among academics as they delve into the astrophysical repercussions of non-isotropy. Our understanding of cosmic evolution might be transformed by an anisotropic universe, which could lead to the creation of new models to explain the alignments we've seen. These models may provide new understanding of galaxy formation and evolution in a universe with such strange features. Beyond the scientific implications, the existence of the axis of evil raises profound philosophical questions. It challenges our understanding of humanity's place in the cosmos. Are we observing a universe that is fundamentally influenced by our own position within it? Or are we merely scratching the surface of a deeper cosmic mystery? The pursuit of answers to these questions reflects our innate desire to comprehend the universe and our connection to it. The spirit of scientific inquiry, where anomalies prompt deeper investigations into the nature of reality. The integration of astrophysics, particle physics, and philosophy enriches our understanding and fosters innovative approaches to long-standing questions. Hypervelocity stars, ejected from black holes and roaming alone. Hypervelocity stars present a fascinating realm of astrophysics, revealing insights about the extreme dynamics of our universe. Ejected from the gravitational grasp of supermassive black holes, these stars can travel at astonishing speeds, often exceeding 1,000 kilometers per second. This phenomenon not only challenges our understanding of stellar life cycles, but also raises intriguing questions about the nature of galaxies and the forces that govern them. The formation of hypervelocity stars often occurs in binary systems. When two stars are in close proximity, their mutual gravitational attraction can lead to dramatic interactions, especially if they approach a supermassive black hole. One star may be drawn in, while the other is flung out into the galaxy at incredible speeds. This gravitational slingshot effect illuminates the chaotic dance of stars near black holes, emphasizing the role of gravitational dynamics in stellar evolution. Such scenarios provoke curiosity. How often do these interactions happen, and what implications do they hold for the broader structure of galaxies? Another aspect that makes hypervelocity stars so mysterious is the connection between them and gravitational waves. Interactions and collisions between stars might cause ripples in space-time that observatories like Virgo and LIGO can detect. Black holes and the stars in their vicinity can be better understood by analyzing these gravitational waves. Researchers can learn more about the interconnected nature of the cosmos and the dynamics between black holes and the stars that round them if they focus on these astronomical events. The chemical compositions of hypervelocity stars can yield valuable information about their origins. Unlike their slower counterparts, these stars often display unusual elemental signatures. The distinct chemical makeup reflects the unique environments they originated from, revealing the conditions in their parent systems. Understanding these variations enriches our knowledge of stellar evolution and the diverse processes that lead to the formation of different types of stars. Additionally, hypervelocity stars play a potential role in understanding dark matter. These stars traversing the galactic halo may provide indirect evidence for dark matter's presence, an enigmatic substance that constitutes a large portion of the universe's mass. Their trajectories, particularly if influenced by dense regions of dark matter, can offer insights into its distribution within galaxies. This interplay invites further inquiry into the fundamental nature of dark matter and its influence on cosmic structures. As hypervelocity stars navigate the interstellar medium, they encounter a variety of environments that can significantly alter their trajectories and characteristics. Interactions with gas clouds or other stellar objects can lead to changes in their physical properties, highlighting the complex relationships between stars and their surroundings. This perspective underscores the notion that hypervelocity stars are integral parts of a larger cosmic narrative, interacting continuously with their environment. The lifespans of hypervelocity stars are often shorter compared to their more sedate stellar relatives. This is primarily due to their higher masses and the accelerated rate at which they consume their energy reserves. As they burn through their resources rapidly, the fate of these stars becomes a topic of significant interest. Will they end their lives in spectacular supernova explosions, or will they collapse into neutron stars or black holes? Each outcome provides unique insights into the processes governing stellar evolution and the dynamic nature of the cosmos. By examining the life cycles of hypervelocity stars, we can deepen our understanding of the intricate mechanisms that drive the universe's evolution, unveiling the mysteries surrounding the birth and death of celestial bodies. Their remarkable speeds often render them difficult to distinguish against the backdrop of the galaxy. Advanced observational techniques and state-of-the-art technology are essential for identifying these fast-moving objects. By refining our observational capabilities, we can unlock the secrets held by hypervelocity stars, advancing our knowledge of the cosmos. When hypervelocity stars interact with other cosmic occurrences, it opens up a new and intriguing area of exploration. Supernovae and the merging of subatomic particles are two events that these stars are associated with. We can gain a better understanding of galaxy formation and the cosmic dynamics by learning how they relate to these more general processes. Hypervelocity stars help bridge the gap between the past and the present by shedding light on their parent system's histories through their remnants. The idea that hypervelocity stars may potentially support multiple solar systems is an intriguing feature of these objects. It is possible that these stars may transport planets into interstellar space if they are able to depart their native systems unharmed. This begs the intriguing issue of whether or not these renegade planets have habitable ecosystems. New insights about exoplanets and the circumstances favorable to life outside our solar system can be gained via the study of hypervelocity stars. The peculiar orbit of Planet 9. Is there a super-Earth lurking in our solar system? Unseen forces have fascinated astronomers for decades as they probe the vastness of our solar system. The unique orbits of trans-Neptunian objects, TNOs, have shown an interesting mystery and are one of the most interesting occurrences. The gravitational pull of an undiscovered large object in the solar system's outer regions may be responsible for the unusually elongated and clustered orbits of some TNOs, according to recent research. These orbits seem to be converging, which might be due to the influence of Planet 9. This concept has far-reaching consequences. It calls into question our current knowledge of the structure of the solar system and the forces that control the motion of the planets and other celestial bodies. If Planet 9 exists, it is believed to be a super-Earth, a class of exoplanets larger than Earth but smaller than Neptune and Uranus. Scientists propose that it could have a mass ranging from 5 to 10 times that of Earth, granting it the capability to exert significant gravitational force on other celestial bodies in the Kuiper belt. The concept of a super-Earth adds an exciting dimension to our understanding of planetary formation. Imagine a massive planet hidden in the shadows of our solar system, influencing the trajectories of icy bodies and potentially reshaping the orbits of other celestial objects. The gravitational influence of a potential Planet 9 extends deep into the Kuiper belt, home to a multitude of icy bodies. The peculiar orbits of some Kuiper belt objects, KBOs, provide crucial evidence for the existence of a massive object situated at a distance of approximately 400 to 800 astronomical units, AU, from the Sun. This gravitational pull raises essential questions about the formation of our solar system. How did these distant objects become so closely aligned, and what role does a hypothetical Planet 9 play in their orbits? Exploring these questions opens doors to new avenues of research, challenging the conventional narratives about the solar system structure. However, finding Planet 9 is no simple task. Its distance from the Sun and potential dimness complicate efforts to detect it. An object situated so far away would not reflect much sunlight, rendering it virtually invisible to our current telescopes. To combat this challenge, astronomers are developing innovative observational techniques and utilizing wide-field surveys. They aim to scan the skies for any signs of this elusive planet. The advances in technology, such as more sensitive cameras and larger telescopes, hold the promise of finally revealing the identity of Planet 9 or confirming its absence. Dynamic models and computer simulations play a crucial role in the ongoing search for Planet 9. Researchers employ these sophisticated tools to simulate possible orbits and interactions between Planet 9 and other celestial bodies. These simulations suggest that Planet 9 could possess an eccentric orbit, taking it far from the center of the solar system. By predicting its location and understanding its potential interactions, scientists gain insights into the history and evolution of our cosmic neighborhood. What will these simulations reveal about the relationship between Planet 9 and the other planets? Historically, the quest for a ninth planet is not new. Astronomers have been speculating about the existence of distant planets for over a century. Early observations indicated irregularities in the orbits of known planets, prompting hypotheses about additional celestial bodies lurking in the solar system. The modern search for Planet 9 has reignited interest in this long-debated topic, connecting historical observations with contemporary research. This continuity in astronomical inquiry illustrates how curiosity drives our understanding of the cosmos. As we ponder the existence of Planet 9, it becomes clear that this search intersects with broader theories about the solar system's formation and dynamics. The NICE model, for example, posits that the giant planets formed closer to the Sun before migrating outward. This migration could have scattered smaller bodies and influenced the architecture of the solar system as we know it. Understanding how Planet 9 fits into these theoretical frameworks can provide essential insights into the processes that shaped our planetary system. The implications of finding Planet 9 extend far beyond our immediate solar system. The discovery of this elusive planet could prompt a re-evaluation of models of planetary formation and migration. It may also challenge our understanding of the distribution of mass within the solar system, forcing us to reconsider how we categorize celestial objects. The characteristics of super-Earths and their potential abundance in other solar systems could also lead to new questions about planetary systems beyond our own. Astronomers and astrophysicists from various institutions and countries are joining forces, pooling their resources and expertise. Initiatives like the Pan-STARRS project and the Dark Energy Survey are pivotal in the quest for this mysterious planet. By working together, scientists increase their chances of detection and broaden their understanding of the solar system's complexities. As we explore the possibility of Planet 9, interstellar influences also come into play. Some theories suggest that this hypothetical planet may not have formed in its current position. Instead, it could have originated from a different part of the solar system, or even been captured from an interstellar environment. Gravitational interactions with passing stars or molecular clouds might have influenced its current orbit. This perspective opens up fascinating discussions about the dynamics of planetary systems over cosmic timescales and highlights the interconnectedness of celestial bodies. The upcoming James Webb Space Telescope is set to revolutionize our understanding of the cosmos. By utilizing advanced imaging techniques and infrared observations, this powerful instrument may provide fresh data that could finally unveil the existence of Planet 9. What secrets will the James Webb Space Telescope uncover as it peers into the depths of our solar system? What is the significance of the peculiar orbits of trans-Neptunian objects in the context of Planet 9? The unusual orbital patterns of TNOs suggest the gravitational influence of a massive unseen object, pointing toward the possibility of Planet 9. Understanding these orbits is crucial for confirming the existence of this hypothesized planet and unraveling its effects on the solar system's dynamics. The ongoing search for Planet 9 serves as a reminder of how much we still don't know about our universe. Each discovery has the potential to reshape our understanding of the cosmos and challenge long-held assumptions. Time crystals in space, stable structures that defy normal physics. Time crystals defy many of the fundamental expectations we have about physical systems, both on Earth and in space. Unlike traditional crystals, which have an ordered structure repeating in three-dimensional space, time crystals introduce a completely new form of matter, one that exhibits periodic structure in time. In a sense, these entities are not bound by the typical thermodynamic rules that govern physical processes. For a long time, the idea of perpetual motion was considered impossible. But with the discovery of time crystals, this notion needs re-examining. Their ability to oscillate without using energy challenges conventional wisdom, raising questions about whether such phenomena could exist beyond Earth and in the vastness of space. In the microscopic world of quantum physics, time crystals possess an unusual degree of stability. Unlike any other material, they defy equilibrium. In other words, they maintain a constant state of motion without ever losing energy. The first lab-made time crystal was created in 2017, where supercooled ions were arranged to form a stable yet oscillating structure. Unlike typical materials that eventually reach a resting state, time crystals operate like a never-ending pendulum, swinging back and forth without losing energy to friction or heat. This feature might lead us to think about cosmic environments where time symmetry, rather than spatial symmetry, prevails. How might this bizarre stability manifest in space? For instance, the universe has an array of extreme environments, such as the event horizons of black holes and the hyperdense matter of neutron stars. These locations mimic the high-energy, low-temperature conditions under which time crystals are generated in the lab. It's plausible to ask whether natural time crystals could form in such cosmic environments, maintaining their perpetual motion as they traverse the vast expanses of space. If time crystals can exist here on Earth, even for a brief experimental moment, could they also form in the extreme gravitational fields of the cosmos? This phenomenon opens up even more fascinating questions about the behavior of matter in space. If stable time crystals could form naturally in space, could they help explain other cosmic mysteries? One might even wonder whether time crystals could serve as a model for dark matter, which makes up approximately 27% of the universe's mass. Dark matter remains an enigma. We've inferred its presence only from the gravitational pull it exerts on visible matter. Perhaps, as some speculative research suggests, dark matter could involve time-like behavior, oscillating in a manner we have not yet observed directly. At the intersection of quantum mechanics and astrophysics lies the question of whether time crystals might offer insight into the relationship between dark matter and the visible universe. To explore these structures further, it's important to understand their stability in high-energy conditions. In laboratories, time crystals are coaxed into existence using lasers and controlled environments, but space offers no such luxuries. In the chaotic environments of neutron stars or near black hole event horizons, particles are constantly bombarded with radiation and affected by gravitational forces. Would time crystals dissolve or thrive in such conditions? Another possibility is that time crystals might form in the wake of the Big Bang, appearing as remnants of the universe's earliest conditions. During those initial moments, the universe was a chaotic soup of high-energy particles expanding and cooling rapidly. The idea that time crystals could have emerged in those conditions and possibly persist leads us to rethink the nature of time itself. Instead of thinking of time as a linear progression from past to present to future, time crystals introduce the notion that time could behave cyclically in some environments. The concept of time symmetry breaking. This phenomenon refers to systems that change in time, but return to their original state periodically. It challenges the more familiar concept of time flowing in one direction. The cyclical nature of time crystals suggests that, under certain conditions, time could loop back on itself, maintaining a repeating structure. This goes against the arrow of time as we understand it, adding complexity to our understanding of the universe's expansion, entropy, and the heat-death of the universe theory. Could time crystals play a role in the fate of the universe? The universe is constantly expanding, but according to some theories, this expansion will eventually slow and reverse, leading to a big crunch. If time crystals can persist across cosmic timescales, they could offer clues about how the universe might behave when approaching such a cataclysmic reversal. It's possible that time crystals might also help explain cosmic inflation, the brief period of rapid expansion that followed the Big Bang. Their ability to exist in non-equilibrium could be analogous to the early universe's rapid changes in both energy and time. Quantum computers, unlike classical ones, use qubits, which can exist in multiple states at once, thanks to the principles of superposition and entanglement. Time crystals offer a unique opportunity to maintain quantum coherence for longer periods, because their perpetual oscillations provide a more stable environment for qubit storage and manipulation. Extending this logic to space exploration, it's worth asking, could time crystals, with their remarkable stability, serve as a basis for quantum computing in space? This possibility isn't as far-fetched as it sounds. Long-distance space travel relies on stable information storage and transmission, something that quantum computers excel at. Time crystals, with their resilience and ability to maintain coherence over time, could enable spacecraft to store massive amounts of data or manage communication between distant parts of the universe. This is especially critical for missions aimed at deep space exploration, where even slight errors in data transmission could lead to catastrophic consequences. The potential existence of time crystals in distant galaxies raises questions about the multiverse theory. If our universe is one of many, perhaps time crystals behave differently across alternate dimensions. In one universe, they might remain stable. In another, they could decay or manifest in forms we can't yet comprehend. This connection between time crystals and multiverse theory brings a new layer of complexity to our search for extraterrestrial phenomena. The study of time crystals offers a window into uncharted realms of physics. Like gravitational waves, dark energy, or the cosmic microwave background radiation, time crystals might reveal clues about the universe's past, present, and future. As of now, time crystals have only been observed in highly controlled lab environments, but space offers a much bigger playground. If these peculiar entities can survive the vacuum of space, they could help answer some of the most pressing questions about the universe's structure and origin. As we journey deeper into the cosmos, the mysteries only seem to multiply, reminding us how little we truly understand. The universe is full of strange, almost incomprehensible phenomena that challenge our very sense of reality. But perhaps it's this uncertainty, the questions left unanswered, that pushes us to explore further. What other hidden wonders await discovery in the endless expanse of space? Keep looking up, because the universe isn't done surprising us yet.